Hello and welcome back to my favorite people, and thank you very much for watching this lecture video. And I'm gonna be talking about carbon-13, and we said this before that whenever species happen to have an odd number of neutrons or protons, it will be active in NMR. And carbon-13 has 7 neutrons, so it will be active in NMR. But there are some issues with it. 99 or 98% of carbon is carbon 12. So we have only 1% from carbon that is going to be active in NMR. Okay, and in order to get really good data from carbon-13, we need to increase the concentration and also run the data collection for longer time. For hydrogen NMR, maybe it will take 5 minutes, while for carbon, pretty sure it's going to be a good number of hours. And sometimes we let it run for overnight or even more longer. It depends how many carbon that species has. And in carbon NMR, the main thing that we care about it will be number of signals that we see, because each signal will represent a unique carbon, and we don't care about the splitting. In fact, we get rid of the splitting because the spectrum will be super complicated to handle it. But it's possible to use it. It's not like it's a wrong thing or impossible. And for hydrogen NMR, we said the chemical shift is 0 to 10, while for carbon is 0 to 225. And similar to hydrogen NMR, if you're dealing with elements of symmetry, then the number of signals will go down. The more the symmetry of factors or elements you have, the smaller number of signals you will get. And it's completely valid about carbon NMR as well. Okay, and here's an example for it. The first molecule, it has 8 carbons. Okay, it has 8 carbons, but out of those 8, because we have a plane symmetry, we're going to see only 4 signals. And the second one also, it has 8 carbon. And by this time, because we change position of the substituent, we're going to get 5 unique carbon. And second molecule, it has 2 mirrors, and those 2 mirrors will chop the molecule to technically 4 parts, and we see only a quarter of it. And so we're going to see three signals for this molecule. Okay, so number of signals will give you a good idea about geometry of the molecule. For example, in these 3 molecules, by one simple NMR, spectrum, I can differentiate them from each other easily just by looking, how many signals are there. Okay. Similar to hydrogen NMR, you will be provided with a chemical shift of the common functional groups. This one will be provided to you during the exam time, and so there's no need to memorize it. But I highly encourage you to practice it, and it's not a bad idea to make yourself familiar to them, similar to hydrogen chemical shift. Okay, let's practice some example. First molecule is C10H12O. And so this molecule is going to be unsaturated. And I go C10H12O. It's supposed to be C10H22. And so 22 hydrogen minus 12 hydrogen. That's going to leave us with 10 missing hydrogens. So that means the hydrogen deficiency index is going to be equal to 5. Okay. And you can say this one is 5 mole of H2. So I go hydrogen deficiency index equal to 5. Okay, now this one you can say is maybe 5 pi bonds, or maybe 4 pi bonds plus 1 ring. And you can keep, actually playing with this ratio until you get, hydrogen deficiency index equal to 5. Okay, now which one is solid? Okay, let's label them. This region, the one on the left, is a carbonyl. That's going to be aryl region. Last one will be alkyl. And clearly I do have aromatic hydrogen, and because I have aromatic hydrogen, so I'm going to say I have a ring. And if I have a benzene ring, that means that's going to give me 3 pi bonds and 1 ring. That one it will be equal to 4. So until now, the hydrogen deficiency is going to be equal to 4. I need 1 more, okay, to make it equal to 5. That means we have 1 double bond. Okay, and it can be CC, or okay, it can be 1 CO. So we have a ring plus 4 double bonds. Okay, next thing is, let's zoom on the hydrogen aromatic region. The hydrogen aromatic region, we see the equation is equal to 4. Well, it's supposed to be 6. So clearly, I have substituent attached to the ring, and I see only 2 signals. So that means my ring here, the aryl ring, it has 2 substituents, and those 2 substituents are across of each other, because in that way I can chop the molecule to 2 halves, and it will give me HA equal to HA. This one is equal to HB, and here I go HB. But those are not going to be equal to each other. X and Y are not going to be equal to each other because I don't have second mirror. And now I'm going to zoom here. What do I see there? And I see a triplet, and integration is equal to 1. So I'm going to say that can be aldehyde hydrogen that it has neighbor or is neighbor to CH2 because it got split to triplet. Okay, and also I have two signals that they have integration of 2 to, okay, and one is a 3 hydrogen, so that must be methyl. Okay, let's propose one possible structure. Okay, so we have a benzyl ring. So I go have a ring, and one suggestion was this to go. We have CH2, and then we have aldehyde. This one will be triplet, 1 hydrogen. That one will be doublet, 2 hydrogen. Okay, and here HA, the integration it will be doublet, doublet, 2 hydrogen. So doublet because of HB, and integration equal to 2. And the same thing for HB, it will be doublet because of HA, and integration it will be equal to 2 hydrogen. And what do I have here? I need to have CH2. This CH2 it will be, okay, neighbor to CH3, so it will be quarter, and the integration it will be equal to 2 on the methyl because it's neighbor to 2 hydrogens. It will be triplet, and integration equal to 3 hydrogen. Okay, let's check the methyl. Is a triplet, and integration equal to 3. This H supposed to be quarter, and it is quarter, and integration equal to 2. And how about this CH2? CH2 I expect it to be doublet, and integration equal to 2. And yes, it's doublet. Why is it has higher chemical shift than the neighbor? Because it's attached to this one. CH2 is attached to a carbonyl neighbor, and that's gonna increase. It's gonna deshield it. And how about the carbon? The number of carbons. I go 1, 2. Here we have 3 of them, so it will be 5, 6, 7, 8 of them. Okay, and let's pass a mirror from the molecule and see whether we get 8 of them. That's going to give me 1, 2, 3, 4, 5, 6, 7, 8 unique carbon, 8 unique carbon atoms. And here you go. I see 8 peaks, and so that's going to match my technically proposed structure. Okay, there are other techniques that we can use in NMR to make actually identification of the unknown samples easier. And one of them is depth 90 and depth 135. The 90 it will give you signal only and only if you have CH. And the 135 it will give you like a negative signal if you are dealing with CH2, and a positive signal for CH3 and CH. So if we see a positive peak, it can be CH or CH3. I see a signal here. It can be CH or CH3. How can I differentiate them? I'm going to get depth 90. Depth 90 will give you signal only if you have the CH. And I do have a signal there. So this one, it will be the correct answer. So that means we do not have a terminal methyl. We do not have a terminal methyl. Okay. And what else? I have a negative peaks. Those are CH2. How many of them? I have 3 of them. So I have 3 carbons that they are going to be CH2, and no terminal methyl groups. Okay, let's go after the hydrogen deficiency of the system. We have C4H8O, I believe. Yes, O. So it's supposed to be C4H10, 10 hydrogen minus 8 hydrogen. That's going to leave me with 2 hydrogens. So I'm going to say the hydrogen deficiency index is going to be equal to 1. Okay, either 1 ring or pi bond. Okay, a ring or pi bond. Okay, and now I do see CH, okay? And if you try to draw a ring, let's see, try to draw a ring, and now that ring has 4 carbon. How many hydrogen? It will be 8 hydrogen, and I need an oxygen. So let's assume we have this. Okay, we have 1 OH here. Okay, and then what else? We have 2 hydrogen here. Okay, another possible structure maybe is this one. Let's say that cannot. Why? Because that's going to be that hydrogen deficiency index is going to be equal to 2. So that cannot be really the answer. Okay, what's the problem with the first structure? The first structure, okay, now I have 1, 2, I'm going to say only 3 signals. Okay, only 3 signals. Okay, well, as you see, we have 4 signals, so that's not going to be correct. So we don't have a ring, okay, because I have 3 signals. 1 is a ring. Okay, I can't have a terminal methyl. Well, I have 4 carbons, and I cannot have CH3. Okay, so it means I need to put something here and something there. Okay, or maybe between those two. Okay, so one possibility, let's have a terminal carbon. And what else? I'm going to say this one maybe is OH. Now let's add the rest of the hydrogens. That's going to be H here. This one, it will be H2. And that one also, it will be H2. So I got here 1 CH2, 1 CH, and 2 here. Like this one also is a CH2, CH2. This structure is matching with actually the data that's given. And you might say, can we move the double bond somewhere in another position? Let's give it a try and see what will happen. And so I'm going to say this is the correct answer, but let's double check other possibilities. Okay, what will happen if I keep this one as this? That's H2 here. And let's put it there. Then we get H here, H, and this one will be H3. So we will get terminal carbon, or CH3 technically. So we should see a peak for CH3, and we said we don't have it. Also, we get 1 signal for here CH, another signal for CH, and only 1 CH2, only 1 CH2, not 2, not the 3, not the 3 of them. And so that cannot be my correct answer, and the correct answer will be this structure. So this one, it will be the correct answer. And this is going to be the end of this lecture, and thank you very much.